Okay, on to section 2.2, Cartesian coordinates and geometrical properties of vectors. The plan in this section is to try to draw pictures. It's a beginning plan. We'll also look at the Gram-Schmidt process. You're familiar with the Gram-Schmidt process from sophomore linear algebra. It involves projections, so we'll have to get the idea of projections up and running as well. Okay. Of course, there's a quote-unquote natural relationship between a point in Rn and a vector in Rn. I mean, we represent them sometimes exactly the same way. A point in Rn is x1, x2, up through x sub n. It's an n tuple of real numbers enclosed by parentheses. Gentle will also use that notation occasionally for vectors. My favorite linear algebra book, Fraley and Beauregard's Linear Algebra, been in print for 25 odd years, distinguishes between points in Rn and vectors in Rn by using parentheses for points and square brackets for vectors. And I'll probably out of habit kind of stick to that notational difference as well. You have to distinguish between points and vectors because they're different things. I may, in these graduate notes, occasionally use parentheses to indicate vectors, really because Gentle does. It should be clear from the context. For one thing, we're probably not going to talk a whole lot about points unless we're trying to do this geometric interpretation thing, but we're going to talk a bunch about vectors. But I'm mostly conscious of this, and we'll give preference to this square bracket notation to indicate vectors. Gentle doesn't go that way. The author of our book doesn't so much notationally distinguish between points and vectors. Yeah, well, in his defense, he doesn't talk that much about points. It's a common misconception to think, yeah, points in Rn, vectors in Rn, same difference. There's a big difference between points in Rn and vectors in Rn. To deal with this common misconception, I like to ask a common question on the departmental linear algebra comprehensive exams. Tell me the difference between a vector in Rn and a point in Rn. Well, here's the answer. What can you do to vectors in Rn? You can add them together. You can multiply them by scalars. They have magnitude and direction. Maybe direction is a concept we'll never make formal. It'll remain an informal concept. We could think of it maybe in terms of the ordered basis, or maybe an ordered orthonormal basis, where there's a first direction and a second direction and a third direction, and I end up getting 3 mutually orthogonal directions in R3, for example. That gives direction some useful intuitive ideas, but formally we'll never define direction. Points, on the other hand, they ain't got directions. They ain't got magnitudes. Points are position, and that's it. Vectors don't have position. Vector in Rn, you can put it anywhere. Of course, we're going to want to represent them with arrows and all that stuff that you're used to. But we can put those arrows anywhere as long as we preserve their magnitude and direction. So vectors don't have a particular position. Points are nothing but position. There's an algebraic structure on the vectors. You can add them and multiply them by scalars. So that algebraic structure is what you mean usually when you say linear algebra. It's the algebra of vectors and matrices. In Rn, the collection of points, you don't have any algebraic structure. You can add 2 points together. You can't multiply points by scalars. Points just have a location, and that's it. So there's properties that vectors have that points don't, and properties that points have that vectors don't, namely location. So big difference between vectors in Rn and points in Rn. As we're getting into this conversation, because I want to draw pictures, I want a geometric interpretation of vectors. We'll say something along the lines of this collection of vectors determines a plane. You say that in sophomore linear algebra. What's that mean? Because the vectors could be anywhere. Does that mean they have to lie in the plane, or what's up with that? we can make such interpretations if we get our setting straight. And that setting is putting those vectors in standard position. Okay, so I want to draw pictures. Whenever I do, and this is my terminology more than anybody else's, I'll have this geometric interpretation of vectors. By the way, vectors in Rn, they have components x1 through x sub n, whereas points in Rn have coordinates x1 through x sub n. The order matters. A vector in Rn is an n-tuple of real numbers. Yes, so is a point. Those real numbers are called components for vectors and called coordinates for points. Let's get the vocabulary out there. So what we're going to do to graph or draw a vector in Rn with components x1 through x sub n is to interpret it as an arrow. We're going to put the tail of that arrow at the origin of this coordinate system, n-dimensional coordinate system for vectors from Rn, and we'll put its head at the point that has the coordinates x1 through x sub n. So tail goes at the origin, head goes at the point with the same coordinates as the vector has components. Vocabulary. Such a vector is said to be in standard position. So we're taking that vector and placing its tail at the origin. We're placing that vector in standard position. Then we can draw pictures. Here's some pictures in R2. We can draw pictures in R3. Ideally, we can use those pictures in 2 and 3 dimensions to try to think about higher dimensions where we can't draw pictures. But we can make analogies. In R2, vector v, in standard position, looks like this. Here's vector v with components v1 and v2. So we'll put the tail of that vector at the origin and put the head of that vector at the point with coordinates v1 and v2. That is, with coordinates the same as the components of vector v. And you see, hopefully, why it's essential I distinguish between points and vectors when I'm in a setting that I've got both of them, because they do look awfully similar. They're different things mathematically. So I need a little notation to distinguish between the two when there's room for confusion, which is when I'm drawing pictures. And I would desperately want to draw pictures because I like visualizing things. Nobody says you had to put that vector in standard position. We could have put it over here in this position, as long as it's got the same, wink, wink, magnitude and direction, because that's informally what I think of vectors in Rn as. We do formally have magnitudes because we've got norms. Direction, as mentioned, direction is something we'll never really formalize. But if I'm drawing pictures, you get the idea. And I'm drawing pictures to more deeply absorb the ideas. Okay, so suppose we drew this vector over here. It now has its tail at the point with coordinates p sub 1, p sub 2. And so the head of that vector must be at the point with coordinates p sub 1 plus v sub 1, p sub 2 plus v sub 2. Same vector, same components for the vector, in a sense the same arrow, different location, because I can put vectors wherever I want to. To get the maximum insight when we deal with subspaces and so forth, putting those vectors in standard position is the only way to fly. So when you say all these vectors lie along a line, probably you're taking the span of a single vector. The resulting subspace is one-dimensional, and all those vectors lie along a line. If you'll put them in standard position, you don't put them in standard position. They can be anywhere in Rn. But to say a one-dimensional space determines a line, you need this standard position thing. To say a two-dimensional subspace of Rn determines a plane, you need this standard position stuff. Without that, you got your vectors all over the place potentially. Put them all in standard position, then you can talk about lines and planes and k-flats and so forth. The parallelogram law of vector addition we can illustrate like this. Take vector v with components v1 and v2, vector w with components w1, w2. You take their sum by definition as the vector v1 plus w1, v2 plus w2. Of course, that has the parallelogram law of addition idea if you'll put all those vectors with their tails, representing the vectors as arrows, put those tails at a common point. Let's put them in standard position. So putting those vectors in standard position, then vector v and vector w determine a parallelogram, and the diagonal of the main diagonal, as it were, of that parallelogram is the vector sum, v plus w. So when we say geometric interpretation, it's likely we're going to have to put those vectors in standard position. That's how we could visualize vector sums. The other thing you do to vectors is multiply them by scalars. So if we took a vector v, multiplied it by 2, we get a vector with the same direction, whatever that means, and twice the length. We multiply by -2, we get a vector with the absolute value of -2, to have twice the length as vector v. And the negative sign has us reversing the direction. There's a little more problem with this direction idea. All three of these vectors are linearly dependent. They're all scalar multiples of vector v. That's kind of the linear algebra importance of them. These two vectors, 2v and -2v, what's up with these? And this depends on the terminology you had in your past. Maybe they're parallel vectors, because one's a multiple of the other. In my favorite linear algebra book, these two vectors are said to be parallel with opposite directions. Some other folks might call these two vectors anti-parallel. They lie on parallel lines, standard position or whatever, but they point in opposite directions. Okay, but direction doesn't have a real clean interpretation. One's a scalar multiple of the other, and in this case, looking at these two vectors here on the right, that scalar's negative. So that has an impact on the pictures that we draw of reversing directions. The pictures are a bit informal, and the idea of direction is a bit informal, but I like pictures enough to deal with that informality. All right, now we want to deal a bit more with bases, our favorite bases. Our second favorite bases are orthogonal bases. Our favorite bases, as we'll illustrate, are orthonormal bases. What makes it my favorite is the ease with which we can compute stuff when we have orthonormal bases. This requires us to look into projections of one vector on another. We can also project vectors onto subspaces. That possibly you did in sophomore linear algebra as well, probably around the end if you got that far. So here we're defining for vectors x and y in some vector space, a subspace of Rn, the projection of vector y onto vector x, projection of y onto x. With this notation, a gentle uses a little hat on that vector y to indicate that it's been projected somewhere. Oops. I'll stick with that notation a little bit. Scroll down, there we go. It's a little bit cleaner than all this stuff here. So I'll use the y hat notation to indicate projections a little bit in the following computations at least. It does become more involved when we're projecting many vectors onto many different things. But for now, we'll let y hat denote this particular projection, and we're defining that to be the inner product of x with y divided by the norm squared of x times vector x. I guess it goes without saying, of course, vector x can't be the zero vector. None of this makes sense. So that's implied by the equation. Could be made explicit. That wouldn't hurt anything. Here's a definition of the projection. Notice that the vector y hat is a multiple of vector x. Here's vector x, and there's a scalar coefficient, inner product divided by a magnitude square. Is this a positive or a negative scalar that's a coefficient of x? Well, the denominator's positive, but inner products can be negative, so I don't know. It depends on the sign of the inner product, and we'll give that some geometric interpretation here shortly. Okay, there's the definition, can't argue with it, but when they say something like projection, you should be thinking something like shadows. And we'll see here shortly that this is the right definition to take with an idea of something kind of physical that's projected onto a certain vector. Okay, but we got the definition, can't argue with it, though hopefully we can inspire that it's the right way to go with some pictures. All right, so take x, y vectors in vector space V, let y hat be the projection of y onto x. Claim is this is the component of y in the direction of x. All right, we're going for a picture. And what we're going to do is consider the inner product of y minus the projection of y onto x, inner product of that with vector x. Okay, that'd be y minus y hat with our notation. Take an inner product of that with x. Y hat's computed explicitly like this from the definition above. Use your linearity properties of inner products. Expand this out. Won't bore you with the details. We'll get this thing here. Here we've got an inner product of x with itself. That's the norm squared of x. That'll cancel with this denominator, leaving us with inner product of y with x minus inner product of x with y. Those are the same thing in the real setting where we are. And so we get the zero scalar out. Zero scalar, right? Right, it's an inner product or scalar product. So of course we get scalars out. So telling you an orthogonality thing. So y minus y hat, say, is orthogonal to x. We know y hat is a scalar multiple of x. So let's scroll down and take a look at a picture. A little early for this, so we need to establish some other stuff. But this is the picture we're going for. So think of x as some horizontal vector down here. And then we've taken vector y and projected it onto that horizontal vector by maybe imagining light shining in parallel rays from directly above. And the shadow of y on a horizontal line would then be this little red vector, y hat. That's the reason they're called projections, because they behave like that, as we're in the process of showing. And we just saw that y minus y hat was orthogonal to vector x. It's orthogonal to this horizontal direction, if you will. Okay, I think we got ourselves a right triangle with angle theta. As we'll introduce angle theta as an angle between y hat and y, or between x and y. And we want to go through and see what that angle theta is, and we're in the process of defining that using some trig. But let's see, we had a right angle here. Let's go one more on the details of that and show what this is. Let's show this is a right triangle using the Pythagorean theorem. Let's take this side squared, that'd be the norm of y hat squared, plus this side squared, that'd be the norm of y minus y hat squared, and this side squared. So we should have the norm of this vector squared plus the norm of that vector squared equals the norm of this, as it were, hypotenuse vector squared. Of course, I got to take norms because the Pythagorean theorem deals with distances. Okay, so that's an X little computation, and it just falls right out. Y hat squared, y hat norm of squared, y minus y hat norm of squared, because this is the sum of the squares of the lengths of the sides. And down here at the end of the computation, there's the hypotenuse squared. So this really works. Y hat is computed like this. So we'll have the norm of that squared. Y minus y hat, that's y minus that norm of squared. Okay, and this first one, we could bring this scalar out front. It'd pick up some absolute values, but remember we're squaring, so I don't need the absolute values. From the x vector right here, we'd get a norm squared of x. When I do the squaring, we'll have a norm of x to the fourth in the denominator. So we'll get a cancellation of the norm squared in the numerator with the norm to the fourth in the denominator. That'll leave us with this norm of x squared in the denominator. The arithmetic is valid, in other words. Let's take this norm squared and write it as an inner product of the vector with itself. And that's how we define norms originally. Okay, expand this out using linearity. That will produce inner product of y with y right here. We multiply the last ones out, as it were. We'd have an inner product of x with itself. There that is. You'd have this coefficient times this coefficient. So we'd lose the negative sign in the product, and we'd square some things. So we get this for the last. I mean, it's kind of like you're foiling it. We'll have an inner product of x with y and an inner product of y with x, with these coefficients popping up both times, giving us a -2, those coefficients, inner product of x with y, or y with x. Those are equal. There is that symmetry. Okay. Hey, inner product of x with itself, that's the norm of x squared. So we could cancel that with 2 of these norms of x in the denominator, leaving us with this quantity here. And lo and behold, we've got -2, this quantity here, plus this quantity, plus another copy of this quantity. So this term, and this term give us 0, leaving us with norm y squared. Yeah. Pythagorean theorem says one side squared is the sum of the squares of the other 2 sides, if and only if you have a right triangle. So we have a right triangle. This is the right picture. I want to introduce angle theta inside this right triangle. And our next plan is to talk about angle theta. All right. In this picture, I've drawn angle theta as if it were an acute angle, an angle between 0 and pi halves. Well, that need not be the case, as we'll see in the picture down at the bottom. But we've got a right triangle. I know the lengths of the sides, we're good on that stuff. And I know I can say the cosine of theta then is the norm of y hat divided by the norm of y. It's adjacent over the hypotenuse. Okay, well, we compute y hat as we've been doing. Okay. Let's see. When we evaluate that norm in the numerator, we get a norm of x. There's a norm of x squared right there in that little denominator, leaving us with a 1 over norm of x. Let's put that in the denominator over here, and leaving us with an absolute value of the inner product of x and y in the numerator. So the cosine of theta from the right triangle can be written like this. All right, notice we base this on a right triangle with an acute angle in it. So the cosine will be positive, and it comes out of those computations. However, the angle might not be an acute angle, and that picture is not entirely correct. So we'll need to do some modifications. Here's what's going on. Y hat is a scalar multiple of x. Right, that coefficient is this stuff here. Say y hat equals a times x, where a is that coefficient. Now, if we take the inner product of x with y, as you know, dot products are related to angles. We take the inner product of x with y, okay? Remember, x was a horizontal vector. I don't know if it points to the right or the left, and that's what's causing us these problems. Then, what happens is we get inner product of x with y. Let's see, y can be written as y hat plus y minus y hat. So actually broke it into this plus that because of the geometry. Use your linearity properties of inner product. That'll give us an inner product of x with y hat and an inner product of x with y minus y hat, which you know this inner product is 0 because we established the orthogonality upstairs a couple times. So we'll get a 0 out for this inner product, and we're left with the inner product of x with y hat. Y hat, we said, is a times x. We can bring that a out front, then properties of inner products. Then we get a times the inner product of x with itself. Inner product of x with itself, well, that's the norm of x squared. So punchline is inner product of x with y, which is related to this numerator here, is scalar a times a norm of x squared. All right, well, is that scalar positive or is it negative? Well, if that scalar is positive, in other words, if this inner product is positive, because we get the inner product over here. So the inner product is positive or non-negative. Then we'll have the cosine of theta, still given by the formula up here. We can drop the absolute values if the inner product is non-negative. And we get cosine of theta is given by this. In this situation, angle theta would be acute. If a is less than 0, we get the vector pointed in the opposite direction. Inner product then will be negative, as we see from this computation here. If we take A to be negative, we'll get an inner product that's negative. Cosine, same computation. Cosine of theta would be the inner product, but we know the inner product's negative, so we get that cosine is less than 0. Well, if the cosine is less than 0, then we don't have an acute angle, we have an obtuse angle. All right, so we get an angle between pi has and pi, if you like. So when that scalar multiple is positive, we get a nice little right triangle. When that scalar multiple is negative and the inner product is negative, well, we've also got a nice little right triangle, but things don't line up between x and y bar quite as neatly. Oh yeah, here, y bar is a positive multiple of x. They're parallel, the red arrow and the black arrow. They're parallel with the same direction. Here, that scalar is negative. Scalar A is negative. Yeah, the red arrow and the black arrow are now parallel with the opposite directions, or they're anti-parallel, depending on your terminological tastes. But we've related the cosine of theta to the inner product of x with y divided by norm of x times norm of y, whether that angle is acute or obtuse, leading us to define the angle theta between vectors x and y as the cosine inverse of the inner product of x and y divided by the norm of x times the norm of y. We can look at the standard basis vectors, and with those define something called the direction cosines, theta sub I, by taking inner products of x with the ith standard basis vector divided by the norm of x, if you like, times the norm of e sub I, but these are unit vectors. So we can define these direction cosines in addition to simply an angle between vectors. Hey, theta is defined as a cosine inverse, so are these theta sub i's. So by their very definitions, those angles are between 0 and pi. By the way we've defined them using the cosine inverse function. They lie in the range of the cosine inverse function. Okay, if we take x as a vector in Rn, this is a piece of cake to write x as a linear combination of these vectors. All we got to do is take inner products, x with e sub I, times those vectors e sub I. This will work if we have the standard basis, that's an orthonormal basis for Rn, allowing us to do these kinds of computations as you've seen before, and we're going to see a bit more of this with other orthonormal bases. But that's how you determine coefficients using standard bases. It's not in the least bit surprising. You just pick those coordinates off. That's what you're effectively doing. And then if we take these theta sub i's, these direction cosines as defined above, we'll actually see that we square each of those direction cosines, square them, add them up. We're going to get 1 out of that. And there's geometry behind this, of course. Here's why. Cosine squared theta sub 1, let's see. Cosine of theta sub 1 would be inner product of x with e sub 1 over the norm of x. Inner product of x with e sub 1 over norm of x squared. Replace the e sub 1 with an e sub 2 and so forth. So here's what we get, as you know how we define the cosines. Now these have in common in the denominator a norm of x squared, so we'll factor that out, leaving us with the sums of the squares of these inner products. All right, a lot of unit vectors floating around. Let's observe the following. Hey, these E1 through E sub n's, this is an orthonormal set of vectors. So if I take the inner product of any E sub I with any other E sub j, that inner product is 0 because they're orthogonal. You can factor this 1 over norm x squared out. You're left with the sums squares of the inner products, and that sum of squares can be written as a particular inner product. It's the inner product of x with E1 times E1 plus the inner product of x with E2 times E2. up through inner product of x with e sub n times e sub n, inner product, there's the comma. So here's the first vector. We'll take an inner product of that vector with itself, which of course is a norm. Are you sure about that? Yeah, when I take the inner product of the e sub 1 term with the e sub 1 term in the second entry, that'll give us inner product of e sub 1 with itself. That's the norm squared of e sub 1. That's just 1 because they're unit vectors. I take the inner product of e sub 1 with e sub 2 or any of these others, those are all going to be 0 by the orthogonality. And we'll pick up only this term. Take the inner product of e sub 2 with all of these others. Well, I get zeros except for the second one, in which case we'll get this term, and so forth. So we can take this algebraic expression, write it as an inner product. Oh, hey, we just said this stuff here, that is vector x. So this linear combination here is vector x. We've got the inner product of x with itself. That's the norm squared of x. So we've produced the norm squared of x over norm squared of x equals 1. So the sum of those cosines, the cosine theta sub i's, sum of the squares of those equals 1. Okay, the fact that we can take a vector in Rn and write it so cleanly in terms of standard basis vectors shows you, how do I word it, it's suggestive of how useful orthonormal bases are. The following theorem elaborates on that a little bit. This technique that works for the standard basis vectors, it works for any orthogonal, or better yet, orthonormal basis. So the claim in theorem 2.2.1 is take a basis, v1 through v sub k, basis for vector space v, the subspace of Rn, where the basis vectors are mutually orthogonal. Okay, so it's an orthogonal basis, not an orthonormal basis. Then the claim is x is this linear combination of those v sub k's. So this is how you find the coefficients in an inner product space when you have an orthogonal basis. Let's look at the proof of that, because you do the same thing in sophomore linear algebra. This is quite straightforward. All right, suppose we have a basis, v1 through v sub k, of orthogonal vectors. Then you know you can write vector x as a linear combination of those vectors for some scalars, some coefficients, c sub 1 through c sub k. They're uniquely chosen. A basis has a unique collection of scalar coefficients such that you can produce the linear combination. That was theorem something or other, one of the results we had. All right, now let's take an inner product of x with v sub I. That is an inner product of that linear combination with v sub I. Properties of inner products allow you to express it as this linear combination. Hey, inner product of v sub 1 with v sub I, that's 0, unless I equals 1. Inner product of v sub 2 with v sub I, that's 0, unless I equals 2. Inner product of v sub I with itself, that's the norm squared of v sub I. That's 1, because, no, I'm sorry, that's not 1, because we're not assuming we have unit vectors yet. I make the mistake because it's common to have orthonormal systems, but yeah, that'd be inner product of v sub I with itself. It's not 0. None of these vectors could be 0 vectors in a basis. So anyhow, all these inner products are 0 except for this one. So that produces c sub I, v sub I, inner product with itself. And if we'll solve this little equation, inner product of x with v sub I equals c sub I, inner product of v sub I with itself, that gives us c sub I equals this. So the ith coefficient must be this, and that's exactly what was claimed. So total piece of cake. We would do this in sophomore linear algebra as well because the proof is so straightforward. So when you have an orthogonal basis, there's how you find the coefficients. You use projections of x in those various directions, v sub I, and then some sort of kind of normalization deal, it looks like. Back to the notes, you know, if you had not just orthogonal, but orthonormal, these denominators, inner product of v sub 1 with v sub 1, that's the norm squared of v sub 1. Yeah, if these were unit vectors, all those denominators would be 1. And then, think geometrically, you could take X and write it in terms of an orthonormal basis, V1 through V sub n, just by taking projection, basis vector, plus projection, basis vector, plus projection, basis vector. All these are projections. These are projections that are a little more straightforward because we have unit vectors. It's easy with an orthonormal basis, if you've got inner products, to find coefficients in a linear combination. So the best kind of basis is certainly an orthogonal basis, or maybe better yet, even an orthonormal basis. Computations in both cases are done with projections. The projection is easier when you have orthonormal vectors. And in this projection, this technique of representing a vector in terms of an orthonormal basis, it's called a Fourier expansion of X, and the coefficients are called Fourier coefficients. Little highbrow verbiage for this setting of Rn or Rk or wherever we are. But if you've been exposed to Fourier series, the same geometry is going on. In a Fourier series, you have an infinite number of basis vectors, they're unit vectors, and they're orthogonal. There's an infinite number of them because you're in an infinite dimensional vector space. But the geometry, even in that infinite dimensional vector space, is the geometry of Rn. Tells you it's a useful vector space. So that's the reason they're using the term Fourier expansion in this sense. It's just finding the coefficients for a particular orthonormal basis. But since you've used these projections, that's the reason they're calling it Fourier expansion. All right, so let's call it quits there. Come back here shortly and deal with the Gram-Schmidt process and the creation of orthonormal bases for a given vector space.